Now I introduce a linear value function approximation. I will show how to use the least squares method to solve reinforcement learning TD problems. To use the gradient method to update the model parameters, we need to define the objective function. This is a quadratic formulation. Here, this is the state value function and the policy pi. In the bootstrapping problem, this is the bootstrapping target. And this V with head is the approximation of this target. This W is the weight vector. We need to update this weight vector in some way to let this approximation closer and closer to his target. This one is the state value function. So if we express this state value function as a linear function of this weight vector, that means least squares method. So use the stochastic gradient method, descent method. We can update the weight vector W from his value at a t step to update his value at a t plus 1 step. Like we mentioned, this is the bootstrapping target, and this is his approximation. So because this V, the state value function, and the policy pi is a bootstrapping target. However, his value is unknown. Right now, suppose we use a Monte Carlo return, to approximate this bootstrapping target. However, the Gaussian this GT is unbiased estimate of the state value function. So if we use n-step return in Monte Carlo, so we got this return. However, this return is a function of the weight vector W. But when we calculate the gradient of this objective function, we assume this target is not a function of the weight vector. So we call this, the gradient is called the Salmon gradient. Salmon gradient means we suppose this target is not function of the weight vector. So if for special case, if the state value function is a linear function of the weight vector, so we can express this state value function as the inner product of the weight vector and the feature vector X. So that means, we can easily get this Salmon gradient equal to the feature vector. Then we modify the W update equation because we use this Monte Carlo return to replace the bootstrapping target. We got this formulation, and then we use the definition of the Monte Carlo return. We got this for the GT. And then we move this feature vector into the squared bracket. And then we got this one. So once the system reaches the steady state for any WT, then we can calculate the expected next weight vector W at t plus 1 time steps. Then we compare this formulation and with this one, and we found B is the expectation of R times this feature vector, and A is expectation of this formula. So if the system convergence, it must convergence to the TD fixed the point that we call WTD. TD here is the temporal difference. So then we can, the TD, WTD satisfy with this equation. And then solve this equation, we can calculate the TD fixed point. It means W is for the TD time temporal difference W. That means this W can be calculated by using a matrix A and a vector B. So use this way, we solve the TD reinforcement learning problem by using the least squares method. For more details, please check with this reference. Thank you.